actually, because we only have 7 downdraft table spots, and if you don't know what a downdraft table is, a downdraft table is a big table with a fan in it and filters, and it actually sucks down. That's why it's called a downdraft table, and it blows out the bottom, therefore it takes all your dust and it puts it on the filters. Okay, at the end of class, when we're all done, we're going to take these downdraft tables out and we're going to clean them all and get them prepped up for next year. So basically it eliminates, I shouldn't say it eliminates, it tries to eliminate dust in the shop. Okay, because if you ever walk into a composite shop, it's basically, you know, a white dust on everything. Some composite places actually have downdraft floors. Okay, and so it all goes down and around and it's gone. So they have a room that's completely set up for grinding on fiberglass. So because of that, we have another project that we have going on, and that is going to be a vacuum bagging project. Okay, and you guys will understand what vacuum bagging is when we get into it. It's a project where you're actually going to build a bridge. Okay, you and your partner are going to have to mentally figure out how to structurally build a bridge, and at the end of our 2-week period, we're actually going to break all these bridges and see whose bridge held the most. Okay, typically it's 1,000 to 1. Okay, so if your bridge weighs 1 gram, it's going to hold 1,000 grams. That's typically where it's sitting at right now. Okay, so that's what we're shooting for, and your bridge can't be more than 150 grams. Okay, so the first year we did it, we didn't put a limit on the weight of the bridge, and I believe, I don't know, cases, I think we were at 700 pounds or something. Okay, so we dumbed it down a little bit, but composites actually can carry an amazing load. So we're going to be dividing into those two things. In our lab times, it's going to be repairing a wheel pant and putting it all back together and regaining the contour and getting it painted, and second is actually building the bridge and getting that so we can actually break them on the last day. Okay, so it's actually a kind of a fun little project. I'll see, I have a bridge here that I built along. So yeah, so basically this is what you're going to build, this little bridge here. You can see I put some strengthening gizmos on the back, and I actually got carried away and put, you know, fines on it, blah, blah. Yeah. That's where it's at, baby. So, we had, a little off topic, but in Senegal, we had bridges that were built by the French. Okay, so this is West Africa. So they came in, and to build a bridge in Senegal is, you know, shouldn't be that big of a deal, but because they were from France, they had to build it according to the France, you know, detailed list of, you know, how to build a bridge in France. So it had to be so high above the water. Okay, they have to have a bridge, and it has to be X amount of feet above the water. So they build all these bridges across these rivers. Well, there's not enough money to put enough fill in to make a nice gradual slope up to the bridge. Okay, so the angle up to the bridge is about like that. Okay, which was really cool for those of us that had motorcycles. Okay, because you could almost get to the other side of the bridge without touching it. Okay, you know, just because at the other side it was going down at the same slope, you know. And so if you did it right, you could, you know, you would let your buddy get up middle of the bridge, and then you could be passing him in the air with your wheels right beside him, you know, before you land. You know, that's what we used. That's how we used to have fun. But anyway, so we're gonna hop onto this. A lot of the stuff that you're gonna need. I can't remember if we're gonna. I doubt we're gonna go to the book, so I guess you don't have to worry about it. You will have to figure out what chapter it's in, because there are things that you're going to have to study, and you're going to have to read that book Grumman X-29, if anybody can read. The only way this airplane could fly is with a computer, okay? They couldn't get a pilot to actually fly because it's too squirrely. But it was one of the very first composite airplanes, you know, the military, they obviously like composites, things like that, so they've been working with it quite a bit. So, let's see. Does this work? Why not? Blank page. Cool. Oh, that's why. So the term composite is a combination of materials that are mixed together to achieve specific properties. Although, this is the next thing. The individual materials do not dissolve or merge completely, but act as one. So there are two things that when you put together, they always retain their own form, per se. Okay? That's the term where you get composite. It's not like, you know, making peanut butter cookies, because when you make all the cookies, they all become one, and then you can't distinguish between each individual part. Okay? The properties of the composite are greater than the properties of the individual materials. So when you get these things together, they are stronger because they're all together. Okay? All right, so let's go to a history lesson. All right, so let me find my page. So the number one goal in aviation is stronger, safer, lighter. All right, and this is according to math. Right? Everybody wants to build it stronger. They want to make it safer, but they also want to make it lighter. Okay. The triplane in World War I. You guys are into wood structures, right? The Red Baron, he flew the triplane. I don't even know what model that was. Does anybody know what? A BR-1? DR-1? So that airplane, it was great and all, but it killed more pilots than the enemies did. Okay? And that was because the ailerons were attached to the rear spar. And the rear spar is made of wood. Okay? So ailerons would fall off. That's a problem. Okay? Anytime ailerons fall off, the FAA they get cranky. Okay? It's just a bad thing. So stronger, safer, lighter. That is the key in aviation. It's also fuel efficient, right? The lighter we make our airplane, the less fuel it takes for us to get from point A to B, which is why the airlines nowadays, you know, back before 9/11 and fuel was, you know, 89 cents a gallon type of thing for jet fuel, they would just fill up the airplane, okay? Because anybody, if you're into IFR flight, if they're coming all the way up here to Chicago and they can't make it into Chicago, they have to have an alternate airport. Well, your alternate airport, they would just, alternate airport, I'm coming from Lauderdale, I'm going to Chicago, I just put Lauderdale, because I had enough fuel to get all the way up here and all the way back. It wasn't a big deal, right? Well, now they don't let them do that, because they got to save fuel. Anytime you throw weight on an airplane, it's not good, so now all the airlines, you know, they can only put as much fuel as they're supposed to need to get where they're going and then get to their alternate with their 45-minute reserve, right? They can't do the whole just load it up and let's go. So the first composites that I can really think of that is back if some of you are into bows and arrows, right? The English longbow was like the most formative weapon ever, right? I mean, it was crazy. I mean, it was a 100-yard machine, and it could actually, you know, do quite well. Well, as soon as you hop on a horse, the English longbow becomes null and void because you have a horse in the way, and you can't draw your bow back and run it. So what was born was the recurve bow. okay? And in order to make these recurve bows strong enough to do their thing, they would add bone and sinew and all these other different things, and they'd you know, wrap it, and they'd make this little tiny short bow like the Arabs used to use, and everybody, you know, used to use on their horses. Because now all of a sudden your bow is super short, and you've got all these things that they mix together, and when they mix them together, it gets stronger, and they were able to get this much, you know, get the same power out of it, only a really tiny bow. So that's kind of like the first one that it really went on, you know, that I can think of that was probably, you know, a composite gizmo, because it was technically a composite, although very basic. So aviation advances are mostly centered around military, right? World War I happens, what happens? All of a sudden, we go from the Wright brothers, which, when did they fly? Anybody know? What was the date? December 17th, 1903. Okay. So they flew 1903, and just a little over 12 years later, you know, World War I happens, and they went from just barely being able to get off the ground to actual aerial dogfighting in an airplane, and they had engines that were producing almost 400 horsepower. Okay, which is crazy when you really think about it. In that short a time, we went from, you know, warping a wing on the Kitty Hawk thing. I mean, that's how they flew, is they actually warped the wing to, they didn't have ailerons, they hadn't figured that out yet. Okay, and then they get to all of a sudden, now we have ailerons, and we got rudders and elevators, and we're cruising, we're up flying 15,000 feet, whereas they barely got like 4 feet off the ground, right? You know, in 12 years, which is pretty impressive. World War I comes to an end. They sign the treaties with the Germans, and they restrict them from flying with engines, right? One of the things in the treaty was saying, well, you can fly an airplane, you just can't fly it with an engine. You know, so what happens there? Everybody starts flying gliders, okay? Which is interesting. We'll get after that in a minute. So World War II comes around. Germans have an automatic military, you know, air force, because they've got all these gliders that were going. And of course, they didn't, you know, comply with the non-engine thing anyways. So they had an air force fired up. What's wild about that is, even after the war, World War II, the glider community stayed strong in Germany. And to this day, if you want to buy the most high-performance glider that you can buy, you're going to buy it out of Germany. Okay? I mean, it's crazy what those guys figured out how to do. Okay? So let's go. So, hang on, I forgot my glasses. I have to go out here a little farther. So basically, World War II, World War I, airplanes were made of what? Wood. They started to make them out of tube. You know, the fuselage were starting to be able to make out of tube. Okay. World War II happened. They started doing what? Aluminum, which is, they call it, what's the word that you guys should know, seeing as you've already done? What's that? Stress skin, okay? So we have aluminum airplanes that are built out of stress skin, right? That's basically where it's at. So now, all of a sudden, rag and tube's gone. It's no longer around. It's all aluminum. So these glider guys, you know, you can only build a glider out of aluminum, but you can't make it as very efficient. Does anybody know what makes a glider so efficient? Keep going. Wingspan. and if you want to register your airplane that you built with the FAA as a glider, the aspect ratio has to be a certain, it has to be a certain aspect ratio before it becomes a glider. What does aspect ratio mean? Yep. Basically, long, skinny wing. Okay? So now think about this. Building a long, skinny wing, okay, out of aluminum, that's not easy. You know, because some of these gliders, you know, they're, the new ones, they're about 1.5 inches thick on the outside. Okay, think about trying to get in there and bucking rivets. Is that gonna, how hard is that gonna be? Okay, it's not gonna be easy. Now let's go back to the aileron. How small are the ailerons gonna be if you have to do that? You know, how are you gonna put these airplanes together? So it was an automatic shoe-in for the Germans to go after composite, because composite, you can build them and you can make super small structures and you can make them super strong, and they're stronger, safer, and lighter. So I have here an outboard aileron off a glider. Who wants to try to build that out of aluminum and make it as light as this? Okay, this is actually a, it's only an outboard aileron, and these guys, Kuhns are pretty smart. I've got another piece I'll show you in a minute, but you can pass that around. That is a highly structural piece, and it will not fail unless you absolutely hit something with it. You can, I mean, it's pretty tough. Okay, but that's why gliders automatically gravitated towards composites. Okay, and if you want to, anybody that wants to get into building a composite airplane, I guarantee you they're going to go to Germany and they're going to be asking questions. Okay, because that's where all the technology is to this day. And these Germans, they're pretty smart. They've done a lot for us. Here's another. I think this is actually a piece of a flat. Okay. This is an insanely high-tech flat. Does anybody know how the F-104 actually can fly? Does anybody not know what an F-104 is? Let me see if I can find it. F-104 starfighter. Let's see. Here. Loading. Oh, is it not doing it on there? Check. Duplicate. Did it go duplicate? Oh. Why am I in the way? Got it. Really? F-104. Oh, that's all you're gonna do for me? There we go. F-104 starfighter. There it is. Okay. You'll notice the pilot is this big. Okay. You'll walk out to these wings. Did it say how big the wings are? Okay, that's what it looks like. Quick picture, right? There it is. You see the. How do I get this? Oh, here we go. Specifications. Here we go. Okay, wingspan. How big is that wingspan? 21 feet. How big is 21 feet? If I go from this wall over here, what's that? 21 right in here, maybe? Okay? 21 feet. That's how big the wing is. Technically, this airplane should not fly. Okay? Because 21 feet isn't enough. Well, first of all, it really can't maneuver too well. You know, it can fly, but it's definitely not a highly maneuverable airplane. It's just a get in and get out kind of airplane. So let's go back to this. So the reason it can fly is because they take air and they pump it out of the top of the wing. Okay, you guys all you understand lift, right? Didn't you guys go through all that? You know, lift. What makes an airplane fly? Money, right? What makes it fly faster? More money, right? But technically it's lift. Lift makes an airplane fly, okay? In order for it to fly, they couldn't get the stall speed down because they had to land at like 200 and some odd miles an hour, you know, which is, you know, ridiculous every time they had to come back. So they pumped air out of the top of the wings, okay, and they made basically vortex generators out of this air. And this air spun around and laid all that flow back down, okay, and it also pumped air across the wing, faking the wings out, thinking that it had more lift, okay. That way they could actually get the speed down to more manageable. I don't know what it was, if someone wants to look it up, but it's like 160. You know, it still hardly can get on the ground. But the Germans, with their glider, they wanted more performance with their glider. And you see these little vents right here on this flash? They actually take ram air in there, and you'll notice there's a little line, and I'll pass this around. It puts air in here and it shoves the air straight out, making mini vortex generators on all your control surfaces, making your control surfaces actually function. Okay? And I mean, I dare you to find a drill that's that size and drill holes like that perfectly, because it is not easy. I'm going to pass that one around. These are some of the things you can do with composites. That's why composites are the next thing in aviation. Okay? Composites are definitely here to stay, and you need to figure out how to work with them. Okay? And I can tell you right now, nobody's going to take you in and let you do a composite repair on their Gulfstream, okay, unless you've gone to school and you've learned exactly how to do it, okay? But if you're working on the boss's Cherokee that he bumped the cowling and he has to have it repaired, you know, you'll be able to fix that, no problem, with what we are going to learn here, okay? That kind of stuff is going to be a no-brainer. So let's see. So glide ratios of gliders, just so you know, the average glide ratio is 40 to 1 on most gliders. They go all the way up to 60 to 1. 60 to 1, they say if you can see it, you can get there. Okay? Which is pretty amazing. So if you're a mile over Ionia on a 60 to 1, you can make the lake shore. Okay? Without lift. Okay? So gliders are pretty impressive. I do recall, you know, I towed a bunch of gliders out of here, you know, at 11 o'clock, and you're like, it's, you know, 5 o'clock, and they're still not back, and you're like, where are these guys, you know? And, you know, finally 5:36, they come scooting back in over the edge, and they're like, you know, oh, we had a fun day, and you're like, where'd you guys go? And oh, Boyne Mountain and back, you know? And so they went all the way to Traverse City and back, okay, in a glider, off of one 2,000-foot tow, okay? So these things are, you know, if you have a pilot's license and you want to actually have fun flying, get into the glider world, because it's actually a lot of fun. because it's you against the air. It's you against the conditions. It's you looking around, figuring it out. And so these long, high aspect ratio wings are what are getting you there. Okay? So the gliders, though, let's talk a little bit about the Germans, and they lost a lot of pilots. Well, what would cause those ailerons to come off on the wood airplane back then in the day? What's that? Anything. Well, where they realize it was coming off is they go into a dive, right? High speed, yes, what is that called? Flutter. Okay? It is called flutter. Okay? Why were most of the airplanes in World War II fabric flight control? They hadn't figured out how to balance aluminum flight controls yet. In World War II, they still hadn't figured it out. They built some, and it would flutter, they would catch, the air just right, and they would just rip right off, okay? Flutter happens so fast, okay? And it's a big problem. So, like, B-29s, it's an aluminum, huge aluminum tube, right? It's a car tube, carry stuff. What are its flight controls made out of? Fabric, okay? I mean, it's crazy to think about these airplanes. Their flight controls were fabric, and they're doing, 400 miles an hour type of thing, because they hadn't quite figured it out. Flutter is a big problem, and I guarantee on those, biplanes, they were, trying to get away from somebody, and they're putting their nose down, and any little movement, even with fabric-covered controls, can cause flutter at high speeds. Okay? When it comes to composites and flutter, it's less than a second and the wings are gone. Okay? Because when that flutter starts, ailerons, let's just say this, so aileron goes up, right? So what does the wing do? The wing's highly flexible, right? So it goes down. Okay? So now it flutters down, now what does the wing do? It goes back up. Okay, a little more than it came back down. And then it flutters back up. Now it heads back down more than it went back up. Now it, so you're chasing yourself, and these wings just go like this, and it happens so fast that they are gone at the wing root. Okay? One of the guys over in, the guy that came over to fix our glider, Baron Sibal, I think I started that one on this side. His boss was doing a test in a glider, and in order to get a certified airplane, you actually have to go past VNE. Everybody know what VNE is? Right? Never exceed speed. Okay, so you have to go so many percent past that, just, for the idiot pilots out there that are going to find themselves in a situation where they're actually going to go into the red zone with their airspeed indicator. Okay, so they want to be a buffer in there so they don't hurt themselves. Obviously if you go too far, you're going to hurt yourself, but most people, the noise and what's going on around them, they realize that maybe you might be going a little fast. Okay? He was doing these tests, and he had to go to whatever percent above it. He was going down in a dive, the wings instantly separated. Now he's in this lawn dart, okay, and it's going straight at the ground, and he ejected with his parachute, and his parachute hit so hard, it took him 2 months before he was out of the hospital, just because of the impact, because they figure he was doing 350 or something, and they hadn't, see at that point, I guarantee now after one of those things, it's more of a, you have to pull the ripcord now instead of, hooking yourself into the airplane, which is what we do typically, is you hook the hook on the airplane, that way when you leave the airplane, it pulls your chute for you, but at 300 plus miles an hour, it's not a good idea to pull the chute. You want to wait till your body gets down to the 120 miles an hour and slows down a bit before you do the whole, you know, I think I'd like to ride slower back down to earth type thing, you know. So flutter is definitely a problem. You guys, you know, you're into, have you done balancing ailerons? I think that's coming up here after painting and things like that. Balancing is definitely a crucial thing. So, remind me what our times are. We started at 12, didn't we? Or at straight up. We started at 1. So how do I get back on track here? So this is good. Let's just take a break right now. Let's give you guys 5 minutes. Let's get back in here and then we'll try to play around with this. At some point we're going to go out and start doing something in the lab here, but I got to get some of this PowerPoint out of the way. Hopefully we'll get to it. With it, I'm gonna top it on the bottom. That way when this thing's clear, I'm good.
You're good, you're done. V stands for velocity. So the VN. Once you use it so much, you'll stop wondering about it.
popular as they used to be. Just the gliding community kind of faded. I mean, we used to do anywhere from 60 to 100 toes every day.
What do you do now?
Nothing? No, we had two girls, two 233s and one 26 online. So we had 5 gliders online, 3 tow planes, and then when the private guys came out to fly, there'd be 8 of them, and so you'd have all those in the air at the same time. And now, what's that? They call me every now and then when it's good weather. We don't do any training anymore. So when you do a training, you don't care, about the weather. You just fly, unless it's too windy.
Do you have anybody certified?
Oh, there's lots of guys around. We just have a glider.
Oh, there's no glider here.
I wonder why Wama doesn't run out the glider.
That's a logistical thing.
I did the annual on that one before this last year came on. Side panel, like inside of the
All right, let's get going again.
Everyone,
Yeah.
everyone.
Huh?
Everyone. Pay attention.
Chop chop.
Mr. Kuhns doesn't mess around.
So we're talking about flutter. Back in the 80s, Ethnos Aviation, which is New Tribe Mission back then, they had a 206 in I don't know, Philippines or Papua New Guinea, somewhere over in that side of the world. The trim bolt, the bolt that holds the trim tab on, the bolt that holds the servo tab on. Do you guys know the difference between a servo tab and a trim tab? Hopefully you've gone through that. So the servo tab actually broke and failed, okay, on the elevator, okay, causing flutter. Pilot couldn't touch the yoke. It's going in and out so fast, okay? You couldn't hold it, you couldn't do anything with it. It was just, sitting there, moving in and out so fast. So you've got people on board, what do? Well, back then they had real pilots, that grew up, in aviation, that, understood aviation. It's not so much anymore. We're losing a lot of pilots, so it's better if you go from the ground up and you work hard and you get tons of flight time and you learn all the bad things that can happen to you, and then you get into the mission world. That helps a lot, because you have experience to rely on. This guy reaches over and he starts using the trim, okay? Because the trim is on the other side of the elevator, right? Even though it's flapping so hard, the trim allowed him to pitch. He was able to use it to actually pitch the airplane up and down. You can't necessarily use the ailerons, right? Because you can't touch the yoke. Okay, so therefore you got rudder, so you can actually kind of steer the airplane a little bit. And he was able to actually get it onto the runway, which I've tried this many times, and it is not a pretty landing to get your airplane back to the runway without touching the yoke, okay? Using only the trim and your rudder. You can do it, and if you're a pilot, I suggest you try someday, because I've heard of numerous things that have caused people to lose, like an elevator control, a 182 if the cables aren't tight enough. Okay, it's possible to jump a cable off of a pulley. Now all of a sudden there's just nothing there. There's no elevator control. So it's only trim at that point. Okay, so these little things as a pilot you need to pay attention to, and think outside the box a little bit, and play with scenarios like that. Also a king air, kind of like your king air out here. The elevator cables run across the main bus right under the floor. I'm not sure if this one has the main bus under the floor, the same as all the other king airs. well, if you don't put the guard back on, the plexiglass guard that keeps the cables from touching that main bus, and the cables bounce at the right time that you hit turbulence or something, and that cable goes down and it barely touches that 24 volts, it's instantly gone, your cable, and now you're sitting there with an airplane with no elevator also. I've heard of that one happening also. So in both those cases, you run the trim. At that point, they still have ailerons, so that helps quite a bit. So you can just use your power and your trim and get your airplane back on the ground. Okay. So flutter is definitely a problem. You know, when you guys are doing your inspections and you're looking at these goofy little things in the back there, you know, and you think, oh, it's not that big of a deal, a little bit of play. No, you want to look at it carefully because that little bolt on the back, if that leaves, you've got some big problems. Let's see. All right, so where are we going to see composites in general aviation or business aviation, wherever? Fairing, wing root fairings, wing tips, all kinds of different fairings, cowlings, things like that, wheel pants. That's where we're going to find all the composites right now. Obviously, if you get to a Cirrus airplane, it's all composite, and nobody's going to let you touch their Cirrus airplane unless you've been to Cirrus school, okay? And you learn how to do these repairs, okay? So, let's go back, now that I'm done online. This guy. Alright, so, stronger, safer, lighter, right? Everybody agrees? I mean, it makes a lot of sense. That's what we're trying to do. You don't want to make it too strong, and you don't want to make it too light, you know, because otherwise you're going to give up safety. Okay? You know, and sometimes too strong is actually a problem, right? You can beef up a rib with a half-inch, you know, piece of aluminum, and now all of a sudden you got stress at both sides. You know, it doesn't, you have to really think about, you know, how to repair airplanes. Okay, so composite advantages, excellent elastic properties, doesn't work fatigue. The G103 is a glider. They put a life limit on the fuselage, it was 8,000 hours. After the first one hit 8,000 hours, they bumped it up to 10,000, and now it's been bumped to 12,000, because every time that hits the next number, they bring it back in, they look at it, and they go, there's nothing wrong with this thing. You know, it just keeps right on going. And there's some gliders out there with some pretty high times. We had one that was 10,000 hours, so. Spent most of its life in Hawaii, skipping rides. So, interesting one, yeah. Very high strength to weight ratio and doesn't corrode. Allows for complex aerodynamic contoured shapes like we just saw. I mean, these ailerons, these little tiny ailerons that you want to build, you know, you can manufacture those out of composites, whereas, like I said, try doing that with aluminum. It's just, it is not easy. Low thermal expansion properties. A lot fewer parts and fasteners. So here we go. Obviously, these are military. Military, they, you know, they're always trying to do that. Yeah.
How do gliders keep their track lifetime? It's not, they don't have engines running the back, you know, how do they keep their lifetime?
The low life ground guy. The guy that runs the ground off. He writes takeoff time and landing time. Because how do I get paid if I'm renting my glider? I want to make sure you've got the numbers right. You know, that way I can bill per hour. And gliders were kind of a cash cow. I mean, very little maintenance on a glider, and you're still getting, you know, 50, 60 bucks an hour, you know, to rent the thing. Plus, they got to pay for the tow. You know, so what you see see here, you see it says boron epoxy. Well, you guys aren't gonna play with boron unless you go to the military or you go do something else, because that kind of cloth is super expensive. But you can see, the weight savings, stronger, safer, lighter, right? Boom, we're lighter. Look at how much, we get to actually reduce the weight of parts by, getting carried away. Now, obviously, these are little parts on the airplane. It's not like the entire airplane. So this is a very old airplane, and I doubt there's any of these flying ever right now. But, this was one of the first ones. The vertical stab was composite. Okay? On that stabilizer, the aluminum one weighed 858 pounds, composite 622, 17 ribs compared to 11, 716 parts compared to 191, and the biggest savings is 40,000 fasteners compared to 6,000. Okay? That's a lot of fasteners that have to be installed in it. If you can do it with composite, it's just a win-win situation. Disadvantages. Difficulty of inspection. Obviously, aluminum, we go out there and we look at it, and we're like, oh, obviously there's a wrinkle. That's a problem. Is a wrinkle gonna show through in a fiberglass part? No, it's not. It's gonna flex and, cause damage. Susceptible to impact damage. Flight AA-587, second deadliest crash in the U.S., was the one that went over New York and lost its vertical. Okay, the vertical attach points are made out of carbon fiber. What they found out on that one, this is just after 9/11, they thought it was another attack, another missile thing, or something weird going on, and come to find out that it was a pilot-induced issue. Okay, POS, or POT, poor operator's technique. POS, definitely POS. It was poor operator's technique, and the reason is because the pilots, everybody that's grown up in aviation, who are all pilots here? Before you take off, what do you do with your controls? Free and correct, and you go all the way, deflection one way, deflect the other. I tried to take off in a couple different airplanes in a Super Cub once. I loaded all my banner gear in there, got it all in there, and I'm ready to go and get down to the end of the runway, and I do my control stick check, and I go like this, it goes all the way that way, and it goes clunk. Because I had set a 5-gallon bucket with ropes right beside the stick in the back seat. Okay? So had I not done my checks, I'd have had no right, stick, which could have been a problem, because everything wants to go left, right? So everybody always goes stop to stop. Well, they learn this going all the way up. They get to this specific flight. They take the rudder, which is powered, which is hydraulically controlled, and they go all the way to the stop till it goes clunk. Then they go all the way to the stop the other side till it goes clunk. Okay? And when you have that much mass and that much hydraulic pressure forcing that rudder all the way over, when it hits that, the moment of that hitting is enough to jar things pretty hard, and they realized that the pilots were doing full rudder deflections before they took off. Now they're only supposed to do, 3/4 deflection, not all the way to the stops, because it fractures the attach points and the tail comes off. Right? So that is a problem. The only other flight that's worse, hasn't beat by, 10 people or so, is the one out of Chicago that the engine fell off. I don't know if you know that in Chicago back in, the 70s or whatever. My buddy that I used to work with over in Muskegon, Victor Braun, his dad actually flew that airplane into Chicago, and then his crew was relieved from that airplane before it took off and crashed. That, by the way, is because in order to change an engine, okay, they had to just take out like 90 90 bolts on the pylon, okay, to pull the engine down and pull it away. Well, said mechanics are like, well, this is dumb. Let's leave the pylon there and let's just pull the two main bolts and hold the engine on. Okay, so they get the forklift up there and they would reach in there and they would pick that engine up with the forklift. Okay, pop the 2 bolts, no big deal, right? Problem is, you go just a little too far, that forklift hits the pylon structure. And you can only hit it so many times before that thing breaks. Okay, so on takeoff, engine off, fell off the airplane, and they couldn't get it back. So, I mean, sometimes we can step over ourselves and we can cause a problem by trying to cut corners, okay? You guys remember the box and the tiger coming in, and the guy sitting there saying, dog, quiet, he's coming, you know, and they're inside the box. Remember that picture I showed you? Okay, well, that's a dog moment big time, okay? And that's not where you want to be. They're also sensitive to chemicals and solvents, all right? You kind of have to stay away with that stuff. Time-consuming manufacturing process, it definitely takes longer, okay? And you need special tooling and equipment needed for large advanced parts. These are the things that are a problem. So here's an F-111 aardvark, okay? It has a composite nose cone, right? Great and all, until you hit a bird. Hit a bird when you're cruising at, you know, just a mile speed of, you know, Mach 1.3. Whatever it, I don't know how fast he was going, but judging by the nose cone, he was moving out pretty good. But that's a bird strike. Okay, so composites can take a pretty substantial hit. That's why you want them on pieces that don't necessarily carry everything, carry all the loads. All right, so let's talk about isotropic and anisotropic. These are 2 words that you need to understand. Isotropic, the material has equal strength properties in all directions. That's aluminum, right? Most metals are isotropic. All right? The other word here is the material strength property depend on the direction that they are measured. And what that really means is that if my fibers, my composite fibers are all going one way, that's the way the load is going to be transferred. It's kind of like, you know, when you see the karate boys, you know, and they're breaking their pine boards, okay? They don't go grab the fancy oak boards, they grab the pine boards, and then they cut it so the grain can snap real easy, and then everybody gets their little chance to go up there and break this little thin pine board, right? Right? And anybody can do it. Alright?
If I would've turned that one out of the day, I'd be crying.
Yeah. Yeah. So it's not that difficult as long as you hit it in the middle. You know, and make sure there's no big knot right there. You know, that's the problem. Composites are anisotropic. Anisotropic. Is that how you say it? We'll just say it. We'll just say it is. Okay. The material is only strong and stiff in the direction of the fibers. Okay, the way composites work. Composites take a little tiny fiber, okay, from over here, it travels all the way over there. It transfers that load from one side all the way down, okay? And because there's so many of them, that load gets transferred all the way down, okay? So if you want something to be super stiff this direction, you're going to run all the fibers this way, okay, because it's going to be super stiff. If you want it super stiff this way, you're going to run all the fibers like this, okay? So in fiberglass, great, I don't want to do that. So in fiberglass, one strand comes over here and it's glued to the other strand, so that strand, you know, transfers the energy into that strand, transfers the energy to that strand, and the energy is dispersed out over a long way. And that's why on gliders, you think that a glider wing has got a lot of structure in it. This is a glider wing. It's cut out. This is the main bar. Okay? The way these things work is the fact that the top skin has energy, it's dispersing energy out, and it's dispersing energy on the bottom side. It's wrapped around all these little things. Just the way it works, it is a fluid movement, and it can flex. It can do anything it wants, and that's why building this versus building out of composites is so much easier than building it out of aluminum. Okay, aluminum doesn't give as much. Okay. So composite properties, fibers are supported in a resin matrix. You'll see that word a lot. A resin matrix. Matrix is only what holds it together. It's the glue, right? The fiber is the primary load-carrying element, while the matrix transfers applied loads into the fibers and holds them in position. Resin or matrix is brittle. Excess resin is bad. Excess resin is brittle. Okay, so if you see a repair that someone's done to a cowling, and they get all done with their repair, and they just keep pouring the resin on there, and they're like, oh, more's better. You know, no, it's not. Okay, it's definitely not better. It does make it brittle. Okay. Composites, they're designed so that the fiber orientation matches the direction of applied load. So we can actually manipulate our composites to carry the load that we want it to carry. Like in this glider wing, okay? They want that load to be carried. You know, there's not so much load fore and aft, it's more lifting, okay? It's more up and down loads. You know, so the top is a compression load, the bottom is a tension load, you know, while you're flying. Multiple layers are used to compensate for varying load direction, right? So closer to the wing root, we might want more, you know, because that's where more load is going to be taken, you know, that kind of a thing. Now what are we on? Structural properties. So this is where I was talking about, we can take different types of fiberglass, and we can rotate the direction of fibers to carry that load, carry whatever load that we've got across what we're trying to do, and make it so it can act a lot more like the isotropic. So using a lot of layers and varying the orientation allows composites to come close to isotropic properties. Notice, it can come close, okay? It can't always get there. But in our world, in aviation, what's the hardest thing we do with an airplane? We land it. When we land that thing, it comes in and hits, that's the hardest thing you can do. When you're flying through the air, okay, you're subject to air loads. It's different. It gives a little, you know, there's a lot of giving that gives. And whereas you land that thing, it's all of a sudden plump, and you are out. And those of you that are pilots, I'm sure every single one of you has plumped it in before, okay? And you eventually learn not to do that. But, you know, that's why the trainers always, every time I see a training Cessna out there, I know if I go look underneath it, that all the rivets in the gearbox are going to be, you know, I'll be able to take them with my fingers and spin them. Okay? I had one lady fly in once, and it was so bad that the rivets had actually, the heads of the rivet, there was a hole as big as the head of the rivet through the skin of the airplane because they had been so loose for so long and just sitting there. The rivets were still there, but the skin that it was supposed to be holding was multi-isotropic material layup. So we've got a 0-degree direction, a 90, a 45, a minus 45, another minus 45, plus 45, 90. I actually am not totally a fan of this. I'm more of a fan of the 60 degree. Okay? Because I want to go 30. I want to go 0, 30, 60. You know, that way it gives me one extra layer, you know, direction that I'm a little more, things can be a little stronger. And that's just my preference. Since the strength requirements are a function of ply orientation and sequence, it's critical that during the repair, each damaged ply must be replaced with the ply of the same material and with the same orientation. It is very important. When you see this here, I've done numerous repairs on glider wings, okay? They'll run over a runway line, so it'll be a gash in the bottom. They want that orientation of that fiber to be in the same, exactly the same as when they installed it. You know, they designed it to work, and it only works that way. And so when you put it down, you make sure that that orientation is correct, to the point where when I am doing a repair, on the side of my repair, I will put a little hash marks of how I want that first layer to be. I want the second layer to be like this, and the third layer like this, and so on. By the way, there's only 2 layers of fiberglass on the top of this. Okay, that's it. Just 2 super thin layers. That's all that holds these gliders in the air. Okay? So if you're dealing with 2 layers, you better make sure it's right. Okay? We also call this the warp clock. It's used in specs, structure repair manuals, and engineering documents to describe the direction of fiber. So call it, let's say your warp clock needs to be whatever. And because of the warp clock, obviously everybody understands a clock, but then when I look at this picture, I'm like, okay, well, there's nothing to do with a clock on here. But it's all in degrees, but they still call it a warp clock. Okay? So this is an example of a repair that was done to I don't know, some weird airplane, but this is the tail section. This is where the horizontal attaches. And so they obviously hit something with, the other side or this side, and it cracked all the way down here. And you can see they drew out their repair. And so these layers in here, I guarantee, are directional cloth that run this direction to give the strength to that horizontal. Okay? Whereas these 3 layers down here and up here, they're probably just going to be, whatever they want, willy-nilly. Probably one's going to be this way, and then you're going to be a 45 and another 90. Whereas these layers in here are going to actually be like a longitudinally to give that more strength to the attached point around the horizontal. Tell me what was next. All right, so let's talk about the types of things. You guys are only going to deal with fiberglass for your wheel pant repair. For your bridge repair, you're going to do a combination. You're going to do carbon fiber and fiberglass. Okay? These are 2 different things. So in order of amazingness, fiberglass starts, it's the first one. Okay, that's what we're going to be using. The next one is Kevlar. What's Kevlar known for? Bulletproof vests, right? So if I were to go over here and I would pull this out, one of the students from a couple years ago, he builds these over in Lansing. Okay, so this is for an A320. This is the fan case out of an A320, and this is what they put in there, and this is 11 layers of Kevlar. Okay, and it's to keep the engine, when it explodes, not if it explodes, but when it explodes, okay, comes apart, it keeps the pieces in the engine. Okay? So this bad boy, he wrote on here, obviously this goes all the way around, and this was one that didn't, it failed or something. It's $5,600. Okay? He went over to the Pratt and Whitney boys over there, and nobody over there could get their composite machines working. And he'd been through composite class with the high school program that I was teaching, and then he'd been through here, and he actually went and got all their machines up and running, and he became the head of the composite division over there because he understood just enough about composites to go where he needs to go. And of course, we talk about bulletproof stuff, so I had my son try to shoot it with a .22, okay? And he decided to hit 2 here, and I'm like, better give that to me so I can put one in the middle for him. But you can see in the middle, I mean, there's very little delamination on the back, right? But what's interesting on the front here, you'll notice when that hit there, what did it do to all that force? It went in kind of star patterns. So it took that energy that was hitting and it dispersed it in every single direction, not allowing it to penetrate. Okay? Now, I've always said I was going to grab the 223 and go see what it'll do. I would imagine that the non-hollow points aren't going to have a problem, but I still haven't tested it yet. But I will at some point to test it to see what it'll do. But it'll be interesting to see if it actually can stop a 223 round with only 11 little pieces of Kevlar. Okay? Yeah. I think it's possibly some of the lead going from the horn. Yeah, like it went in and it couldn't go any farther. And so the way it works is obviously as our impact hits, every time it has to break a piece of fiber, okay, it's getting rid of energy. And when it tries to break one piece of fiber, that fiber is transferring that load to the next piece of fiber, to the next piece of fiber. Then, so it's got to sit there and it's going to start breaking all these pieces of fiber. And Kevlar, Kevlar is pretty amazing stuff. Let's see if I can get a chunk of Kevlar right here. Okay, so this is Kevlar. And it's so fine. Like, so you can actually, I mean, it's so light, and there's so many pieces of it. And that one's got quite a bit, so it actually sank fairly good. But as you can see, you can't measure how thin it is. Yeah, I mean, I'm sure someone can. I'm sure there's machines out there that can measure how thin that fiber is. But it is so thin. The American boys, they were like all excited because they could take they made a drill bit that was super small, right? Okay, and they sent it over to Germany and they're like, here, this is kind of cool, we built this drill bit. Well, the Germans drilled a hole in their drill bit and sent it back. It's just kind of wild that way, because you think you got all the technology in the world, but man, there's other guys that know a lot more. Okay. So that fiber is so thin that it transfers all that load everywhere. Now, if you ever have to do a Kevlar repair, remember Kevlar. Trust me, I hate Kevlar. It doesn't sand at all because it won't give up. It's so tough and so nasty to work with that you have to change out your sanding disc constantly because you need a super sharp sanding disc to cut Kevlar. Okay, whereas carbon's a whole different ballgame. So we got fiberglass up here, and that's what we're gonna be working with, and fiberglass is, well, yeah, so fiberglass is just this white glass, okay? That's all it is, just plain old fiberglass, and it, you know, everybody thinks it's itchy in this form. It is not itchy in this form. It's only itchy when you add the matrix to it, and then grind it, okay? So those of you that wanna grind on your project with short sleeves, okay, and shorts, okay, you will learn really quickly that that's not what you want to do. Okay? You want to have long sleeves, and if I'm going to do a lot of grinding, I'll actually take my sleeves, roll them over, and I'll tape them. Okay? Because I don't, you know, I mean, it's one thing to have itchies on your hands, it's a whole nother to have them in your armpit. Okay? It's a whole different ballgame. Okay? So fiberglass, you can grind all day long. It gives up easy when we grind it. It actually does really well. Kevlar, complete opposite. Royal pain to grind. So we've got fiberglass, Kevlar, and by the way, that Kevlar I showed you was red Kevlar. It's only because it's dyed that color. Normal Kevlar is this yellow opaque stuff. So here's some more Kevlar. So it's this same, it's that same color. So if you see this color somewhere, you know it's Kevlar right off the bat. If it's black, it's gonna be carbon. Okay? If it's a weird color, it's gonna be Kevlar. But it'll be fancy Kevlar, kinda like that stuff. Because you can buy Kevlar in different weaves. So this is a glove box cover that I built for my boat, okay, and I used red Kevlar with carbon fiber, okay? So, I mean, it's great and all, it's just basically for looks. So you can pass that one around if you want. You can even pass this around if you guys want to look at this, that guy. So that's the two things, the top two. Then we get to carbon. Carbon. This is carbon fiber. And this is actually a fancy carbon fiber because this is not your normal, you know, standard weave that looks like cloth. Okay? This is actual stuff I bought. I was going to do a bunch of weird things on my boat with it, you know, because I really like the look of this this hexagon carbon fiber look. And it's good stuff. You have plastic things that are breaking, like on our boat, there's the plastic cover up on the front that we would always step on, and it was always broken. I put carbon Kevlar over top of it. We walk on it all the time now. It's never given up. Okay? It's so strong and so resilient. And it's actually kind of a cool thing. On my 150, I want to take the instrument panels out, and I want to cover them in a blue carbon Kevlar, kind of like that red Kevlar one. And if you want to know how to do that, you can message me. It's kind of fun to play with. So let's talk about carbon fiber. Carbon fiber is a lot more brittle, okay? But it's stronger. It's a lot stronger, but it's not as brittle. Hockey sticks. Today's hockey sticks are all built out of carbon fiber, okay? That's why when you're watching a hockey game and they take a puck and the slap shot comes in and hits a stick, it'll snap it right in two. Well, it's not, you can't take impact damage, but man, can it flex, okay? It can shoot a lot better than your fiberglass. Some hockey sticks out there actually have fiberglass inside with the carbon fiber to give it that more resilient flexibility, I guess. Gives it, it's more, it can handle, even though it's heavier, it does well. It can flex, but it won't, it's not as susceptible to impact. So we will be playing with this stuff, so these two here with the asterisk, those are the two things that we're gonna be playing with. You'll also notice too, that you can, this one doesn't distort near as bad as normal cloth, normal, carbon. But even you just grabbing it, I don't know if I brought another piece. But like, let's see if I got this here. So like this is a piece of that red carbon Kevlar. You can distort it very easily. I can, you know, so when you're trying to make a perfect, like that glove box cover there, you gotta lay that on. Even the little tiny snags that you have on your fingers can grab it. You know, you have to be real careful, you know. It's like I can feel there's something on my thumb and I can, as I put my finger across it, it grabs those threads and it can pull it. So you have to be real careful about not, pass that around too, about not, I'll send this one out. About not distorting it. Whereas this honeycomb stuff here, you can't hardly distort it. But you'll also notice that when I cut this piece out, I tape both sides of it and then cut the center of the tape. Okay, just to keep away from doing the distortion. You know, trying to keep it nice and perfect. Uh-oh, what happened? Boron and ceramic. The only time you guys are gonna play with those if you're working on a fancy airplane. Possibly only a military airplane, because they're the only guys that can afford that kind of stuff. Okay? Over here, we got the other elements of our composites, the matrix systems. We have two types of resins, thermoplastic resins and thermosetting resins. We will be using thermosetting resins. We will not be using thermoplastic resins. And you're gonna have to dig through your book to figure out all that wonderful stuff on because some of your questions on your test are a thermosetting resin does this, where a thermoplastic resin needs to be blah blah. So you're gonna have to work through those to figure it out. A thermoplastic resin is something that when I heat up, it hardens. Or softens, sorry. When it cools down, it hardens. Okay? Whereas a thermosetting resin, it is a weird resin that actually is a mixture. It's like epoxy. Okay? You mix the two together, there's a chemical reaction, and it'll make it hard. Okay? Okay, we kind of went over this. This is fiberglass. It's just the white stuff. And you'll notice they put tape on the edges to cut it. Yada yada. Two types of fiberglass. We have E-glass. This is the cheap stuff. It's called electrical glass. Okay? Whereas the S-glass is the structural glass. So if I'm repairing an airplane, what kind of fiberglass are they going to make me buy? This one. So like when I do repairs on German gliders, I don't even, you can't substitute American fiberglass for the German fiberglass. You have to make a phone call and you have to have them send fancy fiberglass over here so I can have the right fiberglass to do my repair. Okay? If I'm repairing a wheel pant, which one am I going to use? E-glass. I'm not going to spend my big bucks and, you know, get the structural stuff because it's just a wheel pant. So it'll be fine. So fiberglass is often used for secondary structures, fairings, wingtips, radomes. Speaking of radomes, if you do repairs for radomes, you don't put carbon on there. Okay? Radomes will always be fiberglass. They will not be carbon because can your radar see through carbon fiber? Maybe. We'll get into painting class too, and we had a radome that we had to have repaired. The guy wanted it painted because it had some damage to it, scratches, whatever, blah, blah, blah. I took it in, had it painted, and he couldn't figure out why there was a storm in front of him all the time. Well, instead of using, you know, looking at it and figuring it out, they just shot metallic paint over top of the radome, so he had a storm in front of him the entire time. actually buy metallic paint that is plastic metallic. Okay, and so you have to find that, and it is not easy to find, but you can find it, and then you can shoot that paint on there, and now this film goes away. So, main advantages of fiberglass, it's significantly lower cost. Whereas fiberglass, I might be running $13 a yard, just the general mill carbon fiber, I'm gonna be doing, 25 to 30, somewhere in there. So it's basically double the amount for carbon. If you want the carbon Kevlar, it's gonna be $80. That's why when I bought the Kevlar for that, I didn't get too many yards of it, very few. Here's our Kevlar, again, that's the yellow stuff that we use. DuPont. So DuPont maintains exclusive rights for the production of Kevlar. So they're the ones that came up with it, so they're the ones that get to make you pay through the nose. Excellent tensile strength and toughness, poor compressive strength compared to carbon. High resistance to impact damage, super high, by the way. Lower stiffness density and cost than carbon. Special tools are required to cut and drill it. This is where it becomes a royal pain in the butt to work with Kevlar. Okay, so choose your repair carefully. If someone comes in and says, "Yeah, I want this carbon Kevlar, this Kevlar piece repaired," and you're like, "Go somewhere else. Find someone else that can do it." Unless they don't care totally with, if it's not like life or death stuff. Disadvantage, one other disadvantage, Kevlar can absorb significant amounts of water. So you're not gonna use Kevlar for your live wells in your boats. You're gonna use fiberglass. Okay? That's the best one. Here's your carbon fiber. This is just standard cloth. You can kind of tell that all the ends here match all the ends there, therefore it is the same thing.
What are the special tools you use to work with Kevlar?
Lots of sanding there.
What about like cut and drill it?
You have to have the sharpest, like almost like to buy 5 brand new drill bits. Like the best you can buy.
Then throw them away when you're done kind of deal?
Well, no, you can use them for all the other stuff you want, but as soon as they lose their edge, they don't work.
Gotcha.
Well, fiberglass will drill really nice. You'll be able to put perfect holes in there, and even carbon fiber will be just like that. It'll be amazing. But as soon as you get to Kevlar, there's all these little strings hanging out. But yeah, you gotta use the sharpest thing. To the point where even when you do get little fuzz that's sticking out, you gotta take your brand new razor blade and attempt to try to cut those off, and it's still not easy. Put a brand new blade. It's royal pain. By the way, there is a difference between carbon and graphite, but they're interchangeable. Okay, that's just the way it works. They're used in structural repairs. Obviously, you have to read the manual. Fiber is strong, stiff, and brittle. Carbon is corrosive to aluminum. Problem. What are most airplanes built out of? Oh, now we have another set of problems. Okay? So when they're bonded together, you gotta be real careful. Good compression strength, very rigid in matrix, and high fatigue resistance. What is the problem with carbon again, though? Impact. Any sharp impact, that's the problem with carbon. It can disperse a lot of loads, but it is susceptible to impact damage. Kind of like, the airline's flight that the tail fell off. You can only turn that rudder over so many times before it has a problem. Okay, these guys here, we're gonna go through quick here. Boron, it's a tungsten filament. And anytime you see that word tungsten, it's the same as play with it. Um, And it's amazing. I mean, it's extremely hard, hazardous to work with. So is carbon fiber, by the way. So when you guys are grinding on your carbon fiber, you know, just make sure you have your vacuum going, and we'll get into that as we get there. Um, it's not like crazy bad, but I can't remember, I mean, it can cause long-term issues if you're using it every day. Kinda like the guys working in the asbestos mine, you know, they outlawed asbestos, right? Because what does asbestos do? It gets in your lungs and it stays there, right? Well, they outlawed it, and the reason that it was killing people is because when you worked in a place where there was asbestos, you couldn't even see across this room because there was so much dust in the air from the asbestos, okay? So you breathing in a little asbestos doing your brake jobs, probably not gonna cause a problem, okay? But I mean, you can get, you know, mesothelioma and all kinds of other weird, you know, diseases from asbestos that can cause hazards to your health. Extremely expensive, go figure. Also, ceramic, that's the next one. Extremely high temperature application, right? This is insane. Retain most of its strength, up to 2,200 years. That's pretty impressive. I mean, what does metal melt at? What was our flame torch? Anybody remember how hot our torch was? It's like 5,000 or something, 6,000, somewhere in there. You know? So, I mean, that would kill it, but metal melts, you know. So the fact that this thing here can handle that kind of heat, I mean, exhaust gas temperatures on airplanes only run 1,400 degrees. You know, so that's the hottest thing on an airplane. So you can imagine they're probably going to use this stuff where? In engine compartments. Or, you know, probably out at, you know, exhaust of jets, things like that. Composite part wall. All right. When did we take a break last?
About an hour.
Yeah, we'll pick this up here in a minute. Yeah. Yeah, right. Yeah, why don't you guys take 10 minutes? Be back here at 10 till.
You're a champ, man.
And then we'll do our last 30 minutes, and then we'll see how far we can grind out. Yeah, then you can clean up, and then we can see how far I gotta go to. Is it, so it is lead? Yeah. I mean, if you ever shot a metal plate with it, with lead, it goes everywhere, so that's probably what's going on.
It's just splattered.
BK?
No, it's, so he's, you know Rob Turner? He's on the side of the road. He runs his own show. He goes gun shows and stuff. You know, real 5 times 6.
Yeah, why don't you do it?
If that's cool with you.
Yeah, just,
Just throw a few random things at it, see what it does.
yeah, do a hollow point first.
Yeah.
You know, and try to split it up.
Yeah, and then mark
The
it.
full metal jackets, I put down here somewhere, you know.
Yeah, I'll go like 22 and then just work up from there.
As long as we don't destroy the roof.
Yeah. Like leave pieces of it. No problem. I was just like,
Oh, now that sounds like,
It'd be interesting to see if it's 45.
that'd be cool. Yeah, yeah, it's like fast and slow.
Yeah, 45 lead, see what we do.
Yeah.
I would imagine it wouldn't go through.
Okay.
You don't wanna put it up against a,
I would just set it, yeah, I'd set it in kind of on the grass or
yeah,
or on a table or something,
Yep.
link at it.
yeah, do that.
If you don't mind.
Yeah, do that. Then we can get a good example of what it does.
Yeah, so it's pretty thin stuff, but I mean, it hardly came apart from the point, you know, there's
Right.
barely anything at all.
Yeah, interesting to see what a hollow point,
Yeah,
2 through
'cause
3.
it'll just expand.
See if that'll do it.
Yeah,
I mean, it's got a lot of, copper in it, so
Yeah.
it might decide to go right through.
It could, yeah, depends on
But I've always
if it
wanted
wants
to
to
try.
expand. Yeah, so,
So,
yeah, he's got all kinds of stuff, we can try some green tips. I've got an incendiary for a Mosin, maybe. So that'd be kinda cool, but,
yeah,
All right,
see,
cool.
see what it'll hold.
yeah, it'll be Thursday that I'm going over there next,
Yep.
so
Yeah, that's fine.
I'll bring it back there.
Yep, we'll have a good little show and tell on
Yeah,
it.
that'd be cool.
Tire pin.
So this piece of carbon, there's fiberglass here.
Pretty close.
This is gone to space. Made 120,000 feet. We sent it up with a weather balloon, because it was our rudder, to try to hold it straight. We realized the first time that we sent it up, it was spinning for a bit, so we put a rudder on it to try to keep it, try to keep it from spinning too much. But there's no air at 120.
Hey Siri.
So it's quite
Maybe it's, hey Siri.
Did it stop
It,
it?
it, it, at lower altitudes, it definitely slowed it down, otherwise it was still.
It sounds too much like.
It slowed it way down, so you could actually see what's going on.
No.
But from 120, looking straight down with a
No.
GoPro, you could see
Hi Siri.
Lake
Don't
Erie,
you lie.
Oh, I'm the
you
one.
know, and, the bay, we were just looking straight down. But 120 is really not that high above the earth. So,
Really high for.
but it's still, it's been up there, and came back down.
Oh my goodness.
So,
Trying to do that, bud. And while you eat my battery, you know you'll trick my nose.
are two things that are mixed together. We're starting to understand that, anything that we have, whether it's fiberglass, Kevlar, carbon, boron, anything, it has threads, basically, right? Okay, so individual fiber is called a filament. So those are actually filaments, those little things there. So we call them, a light bulb, in a light bulb, we call that a filament too, right? Okay? Strand may be used to describe a single glass fiber. Are we ever gonna be describing that? No, we just need to know that when someone says it has so many strands, we understand what the word strand means. Bundles of filaments are called tows, yarns, or rovings. Yarns may be twisted in fiberglass or straight. What's aramid? Kevlar. Okay? Anytime it's yarns are referred to as in Kevlar, they're always straight, not twisted. Tows and rovings do not have any twist. Rovings is a term you will see most often. Okay? Groups of tows, yarns, and rovings can be grouped together to form fabrics. Okay? So that's the basics of how this fabric gets to where it is when you purchase it from Aircraft Spruce. You're not gonna be dealing with all these terminology. You're just gonna buy, 8-ounce fabric. Okay? When they say you're gonna buy 8-ounce fabric, that's how many ounces it weighs per yard. Okay? When you buy it from Germany, it'll have a dash number, and if it's got on the end of the number, it'll be like, 125. And then the next number will be like 180. Well, 180 is a lot heavier fabric than the 125. Okay? So over there, it's probably metric of some sorts, but that's how it's graded, like 145, 180, things like that. Fabric styles. We have chopped mat. Let's see, do I have a chopped mat? This is a chopped mat. Basically, it's all different pieces of fiber, and it goes every which way. Okay? There's no cloth in this. Okay? It's just pieces everywhere. That's how they make both. Right? Because it's the cheapest thing to do. Okay? If I flip this over, the other side actually has more cloth. It's actually, has the actual lines. So therefore, if I look at this, I can actually see that the lines all run this way. Therefore, where does my strength? Is it strong this way? It's strong up and down, okay? If I were to take one of these pieces, flip them over, oh, look at, we got carbon fiber, and it's all weirded out inside there, okay? And then we got more. I mean, so I really don't know what this was making, but all these different layers in here make, when matrix is added to it, makes this insanely hard, only 1/8-inch thick piece. Okay? So if you see 1/4-inch fiberglass, there's a lot of glass in 1/4-inch fiberglass. Most fast boats are all 1/4-inch, okay, because they take a beating. Okay? So there's no specific fiber orientation. Very little structural strength, but it's rigid. Non-structural fairings on older aircraft. We don't typically use this stuff in aviation except in wheel pants. Okay, so when you guys, some of your wheel pants that you're going to be working on out there, you're going to see this type of fiber. Okay. Very limited use in modern composites aircraft due to low strength and high weight. Okay, that's another picture of it. Perfect. Fabric styles. Okay, this is where you need to start understanding. I'm going to see if I can get to this. Okay, so unidirectional tape. So in other words, uni stands for what? One direction, right? Not the band, but any of this stuff. This is unidirectional tape. They're the same direction. They may have some fine threads running across to keep the toes in place on the roll. Okay, otherwise all you got is just a bunch of fibers all out there doing nothing. And so they'll run, stitching across it just to kind of hold it together so you can actually use the stuff. Okay? Very high strength in the direction of the toes, but virtually no strength across. Right? Because all that's holding it across that way is going to be the matrix, the resin. Okay? So here's an example. I don't know if this picture really does it any well. No, it doesn't do anything. I don't even know why it's there. We'll go to the next one. Okay, bidirectional fabric constructed with reinforcing toes woven together in an interlocking pattern, much like the clothes that you have on, right? You got threads going this way and threads going this way. Nobody wants to be running outside with threads only going one direction. Okay? It's not going to work. There's going to be too much visually going on. Generally, they have the same number of toes, the same number of threads going, filaments going one way and going the other, right? That way we have strength straight up and down and straight horizontally. That's why we talk about that warp clock. We can take that fiber and we can rotate it. Now all of a sudden we've got strength going this way and this way. And that's why I say I don't like the 45. I like the 30. So I'll go 30 and then 60. And keep on going around. That way I have more directions that the strength is actually working to help me prepare the part that I'm trying to repair. Okay? Because sometimes you don't totally know where the structure needs to be, right? You don't totally by looking at it, you're like, well, it could have forces going this way or this way or this way or whatever. So the more clock angles you have, better off you're going to be. They're slightly lighter than 2 layers. Minimizes resin void. That's the problem. You want to make sure that you don't have any voids in your resin. That negates the strands hooking up to the next strand and giving you the strength that you need. Okay? Voids are a problem. They naturally hold the fibers to the correct orientation during processing, so we don't need those little other strands running across it to hold it all in place while we're using it. Kind of like that piece that you guys were messing with. So here's a good example. Bidirectional and unidirectional. Alright? And a lot of times you actually have to look at it to verify what's going on. So the unidirectional is going to have little tiny pieces of thread that cut across it just to hold it in place so you can actually get it onto your piece. Kind of like that one picture that we saw with in front of the horizontal. Those 2 that run the length of the airplane. There was 2 or 3 layers. That's going to be unidirectional, and those are the ones that are actually carrying the load for that horizontal attach. Oh, nice. Okay, so this is something you're going to have to deal with because in your book it's going to ask you questions of this, so you need to know this is the warp, this is the fill, and that's the selvage edge, and this is the bias. Okay? Bias is the cross directional. That's the direction that it's going to be the most flexible. Okay? This, you need to remember this when you get to your bridges. Okay? And let's say on your bridge, you're building, what do I do with my bridge? So on my bridge, I put 2 little V's in the bottom here, right? Okay? If I were to take the cloth that has lots of threads going this way, it's really hard to get it to lay down here, up over, and lay down here, up over, and lay down because it wants to stay straight. Okay? If I were to turn that cloth and go bias, okay, now that strand is coming down this way and coming over, and it lays into your V's a lot better. So you need to think about that when you're building your bridge, you know, and how, if you're gonna put any kind of structure on the bottom, okay? It's easier to run it in the bias direction. Now, am I gonna get as much strength, you know, going this direction as I would? I'm gonna lose some, but because of the manufacturing difficulties, I'm going to, you know, run some of that this way and also run some longitudinal runs, you know, this way, just to, you know, you gotta start thinking like an engineer and thinking about, okay, where is the force being applied? Because we're gonna be putting this on a frame that sits like this, and we're gonna be putting a hole in the middle, and that's where we're gonna be putting our weight. And so this little tiny piece weighs 113 grams, and it'll probably hold, you know, 80 pounds. Okay? And there's nothing to this. It's super light. Okay? So this is where you're gonna have to start, when you get to your groups, you know, you gotta really sit and think about, okay, where do we want these loads to be transferred to? Because that's what fiberglass does, composites. It always transfers the load somewhere else. Okay? So keep that in mind. So, there are different kinds of weave, okay? Kind of like the difference between crochet and knitting, okay? It's two separate things on how they take the fabric and hook it together, okay? And in your book, on some of your questions, it's gonna talk about this. So plain weave, each warp and toe passes over and then under and over, okay? When you're talking about a satin weave, it'll pass over and then go under, and then back over, okay? And that's the difference between a satin weave and a plain weave. So when there's one of your labs where you have to come up here and you have to identify all these different pieces of fabric, and you only get so many things to choose from, okay? And so you have to be able to look at the fabric and see if it's a crosshatch, perfect crosshatch pattern, or if it's an over, under, over. So like that one piece of fabric, this guy here, this is in the hexagon shape, right? Okay, is this going to be satin or is it going to be plain? Because remember, a satin is over, you know, under, over, whereas a plain weave, you're not going to get this kind of pattern if you have just a plain weave. You can't make this pattern unless you have somewhere, somebody is going under, over, and then under, over, you know, that kind of a thing. Okay, so therefore this would be labeled as a satin weave because it's not over, under every single time. Over, under. Okay, so keep that in mind. That's one of your questions, I think, in your exam too. They ask you that. So also it says satin weaves are used when the fabric must be draped into complex shapes with a high degree of smoothness. So this is where that going to the 45 thing, you know, the bias helps get down through there. The satin weave will help do that also. So here's an example of all your weaves. So therefore, and they call this an 8 harness satin weave. 4 shaft satin weave, 8 shaft, 5 harness, crowfoot satin weave. Okay, so these are all different kinds of weaves, whereas this is just a plain weave up here. It's just a wicker basket, right? That's the way it works. Okay, so even though there's just all kinds of different weaves when you're talking fabric. So if you're actually going to go fix an airplane and they tell you to use a satin weave, a crowfoot satin weave, you've got to replace it and repair it with a crowfoot satin weave. Okay, let's go. Let's see if I can go all the way down here. That's far. Okay, non-woven Yeah, they can combine multiple layers, basically what's going on, and I think the next picture, there we go. So that's basically what's going on. So we've got, these guys are running like this, these guys are running like this, these guys are running like this, back to this again, and then the final one is on top, okay? When they build windmill, the windmill blades, okay, they're using this kind of fabric. It already comes pre-made from the factory, and it's already stitched together. Put it in your mold, do your thing, and it comes out as a windmill blade. Yeehaw, right? So, and there are some advantages to this. The biggest disadvantage is getting saturation with your matrix. Because now all of a sudden you have to get that resin all the way through all of those layers without having any voids. Whereas if you lay one layer on, make sure it's, saturated, another layer saturated, you know everything's saturated. But if you do it this way, you use this stuff, it's hard to know if all your air is out. Any air bubble in there, it's not transferring that energy. Now you've got a problem. So hybrid cloth. So I already showed you hybrid cloth. That's the Kevlar carbon fiber. Okay, so that's supposedly the best of both worlds. In the glider cockpits these days, everything is all this hybrid cloth. Okay, like, because obviously, even in normal airplanes, what is the most overbuilt structure of the aircraft? Where the people are at, right? Because that's what we want to try to, when it crashes, we try to keep all the pieces and parts inside there, so it makes, identifying people easier, right? We try to, that's why seatbelts are in there, they try to keep things, most of the bodies in the airplane so we can actually get an idea of what's going on. Then they can try to figure out why it crashed after that. Seatbelts don't do any good above 120 miles an hour anyways, right? May as well not even have a seatbelt on, right? But most, in the glider cockpits, they overbuild them and they try to make this capsule strong enough that it can withstand a lot of stuff. That one glider that those two old German boys were working on, guy, he had flown out of here and he had landed out, he couldn't get back, so he had to land in a field. He didn't see the power line. So the power lines, he went into the power lines and, let's see, so he went right in the middle of the two power lines. And so his nose went under the power line and the wings went over the power line. So the power line rode up the canopy until it couldn't handle it anymore and then just went right straight through the canopy. So they had a lot of clean out in that glider before they were able to work on it. So, flying is, there's a lot of things about flying that are, can be dangerous, and you need to be, we all take the risk, when we throw ourselves down the highway at 80 miles an hour, every day, it's crazy what we do nowadays, with our cars and stuff. But we are very fragile human beings, and any little problem like that will cause issues. That one flap that you guys were passing around, that came off a glider that went in just off the end of the runway, and that was his last flight too. So, it happens up there, and usually it's a pilot problem. Very rarely is it maintenance induced, but every now and then it can be. So that's why mechanics need to be pay attention to the detail. It's all about the detail. It's all about using the right thing to repair it. All right, so Cirrus wants to build an airplane, and they had issues because what about lightning?
Need T-sparks.
No, they solved it by doing, they're susceptible to lightning strikes. But so many different types of lightning. We need to take that lightning and we need to disperse it and get it out of the airplane. Okay? We do that by putting metal mesh layers and possibly conductive paints, although those don't work very well, and coated fabrics. But this here is the norm, putting a mesh in it. So now that you've got an airplane that has mesh in it, you have to do the repair, then you gotta put the mesh back on it to make sure that mesh, you know, is hooked to the other mesh in the area, right? So it starts to get very complicated, because you have to recreate the electrical conductivity to make sure that that lightning strike goes away. The Pilatus over here, he got tumbled in a thunderstorm, probably 10, 15 years ago, and took his airplane in for inspection, and they said he had a lightning strike. And the only reason they could figure out he had a lightning strike is there was two little 1/4-inch holes in the elevators where the lightning had exited the airplane, you know, and then they had to go through, they figured out a way that went in the prop, therefore the engine had to get torn down, $140,000 later, they replaced a couple bearings, you know, and things like that, because that lightning went through the engine, through the gearbox, all the way to the airframe, all the way down the other end of the airframe and out the elevator. You know, so I mean, it's a pricey thing for, you know, lightning. So this is an example. My son is down at Gulfstream, and he just went through their composites course, and I told him to send me a couple pictures of him doing the grinds, and you can see this mesh right here? That's a copper mesh that's over top of the composites, okay? So what he's done here is he's removed the paint and primer all the way out to this spot here, and this is where the mesh is gonna get repaired, okay? And then his actual repair down to where the hole was that the instructor jammed in it with a screwdriver, you know, he has to go in and repair that. This is only got 2 layers of carbon fiber on it. You can see the first layer stops here, and the second layer stops there, okay? So this is in between the engine and the fuselage. These are by the nacelle plates, and so they had a whole bunch of them, and that's what they were doing their repairs on. But this is an example, I thought it was a good one, because it showed the mesh that he's ground away to get down to the mesh so he can do the mesh repair on top of it. Even though in that class they actually didn't do the mesh repair, they just did the carbon repair to the honeycomb structure. Ooh, someone else left that in there. We're gonna start with this. Okay, so the resin matrix. The resin matrix is the heart of the composite material, okay? Primary purpose of the resin matrix is to transfer loads from one fiber to another and hold the fibers in position so they can do their job. Their job is to carry the load. The resin does not carry the load. It just facilitates the fibers to be able to carry their load. All resins require a catalyst or a hardener to turn them from a liquid into a solid, right? There's a specific ratio of resin to catalyst required to achieve proper curing strength. Let's just keep on going. Pot life. The specific time, and pot life isn't, you know, the whole, you know, pot life, you know, it's the specific time in which a catalyzed resin must be used, and it can vary from as little as 15 minutes to as long as 8 hours, okay, depending on what you're using. Some of the resins that I've used in the past, I'll take fast hardener and I'll take slow hardener and I'll mix them together, because the fast, it's already hard at 30 minutes. I need longer than that to work on my project, okay? If I use the slow hardener, it's not even starting to set up till tomorrow. I don't want that either. I need it to be ready to work on tomorrow. So I'll mix those two together and make it work. The stuff we're using, we're technically using slow hardener, but we we figured out last year that slow hardener is still way faster than we want to use, okay? So you cannot, the pot life on the resin that we're using is actually fairly quick, okay? It's like an hour, okay? You'll give it a good solid hour of working time, okay? Okay, so the ratio of fiber to resin matrix for the greatest strength is 60-40. Okay? In other words, okay, here we go. 60-40. You'll see that on your wrist. So we're gonna get into thermal setting. We're gonna wait on this because we're really close to being done here. So tomorrow we're gonna hopefully cruise through the rest of this resin stuff, and we're actually gonna get out and we're gonna break our wheel pants. And I have a list up here of our groups, and the groups are identical to the welding groups that we have. Okay? So that is what has been handed to me. So each group will have their own wheel pant. Tomorrow we will destroy the wheel pant, okay? And then you will be required to rebuild that wheel pant and put it back together, okay? So that's what we're gonna be doing tomorrow. We're also gonna go into a little bit of how we're gonna do the repair. We'll get there, but at least tomorrow we'll break up the day by having a little bit of time in the middle that you guys will actually go over and showcase your extreme talents with a hammer.
Do we smack our own project or somebody else's?
You smack your own project.
Little patch, right?
And I gotta tell you, you guys think that this stuff is easy to break, but I don't know. I don't know where it went. Oh, right here. You guys think this fiberglass is gonna be, easy to break, but it's actually not. You can smash it, and you try doing that with your aluminum. With your aluminum project, try hitting it, bending it. I don't know if it will. I went to katana school and they took a hammer and they said, here, hit that as hard as you can. And you just found myself hit it out. You went to katana school? Yeah, he had a London. Not swords. Not swords. And you'll have to bring that up to Nick. Nick is
We're gonna get this one. This